In this part of the Phasor video series, we'll be looking at the behind the scene how these complex numbers actually work to give us the real results. We have seen that a phasor can be represented if we animate this thing. This is actually e to the power j omega t. It's a anti-clockwise rotating line which is rotating at omega radians per second, and we are going to call this thing as a positive frequency phasor. And everything in frequency domain or phasor domain is actually something about phasor. Either it could be its magnitude or it could be their angle. So anything you draw in frequency domain actually represents some information of the phasor. So this phasor is rotating in anti-clockwise direction, so we are going to call this phasor as a positive frequency phasor. Now coming to if the phasor is rotating in anti-clockwise direction, we are going to call it a positive frequency phasor, and if it's rotating in the clockwise direction, we are going to call this thing as a negative frequency phasor. So this thing, the equation for this phasor is e to the power minus j omega t, and the equation for this thing is e to the power plus j omega t. So we have two counter rotating phasors, and if we combine these two phasors together, we have a real signal. For example, cos omega t can be represented as, this is a cosine wave, it's a perfectly real signal. It's actually composed of half e to the power j omega t plus e to the power minus j omega t. And if we plot this thing, this is positive frequency phasor. So if I draw a frequency axis, so this phasor over here is actually rotating in anti-clockwise direction, and this phasor, it's a negative frequency phasor. I draw it at minus some cycles per second, and this thing is rotating in a clockwise direction. If we add these two complex signals together, their sine part will cancel out and we have the cosine part remaining. Similarly, if we have a sine omega t, and that is composed of e to the power minus j omega t, and it has a phase shift of j, and the positive frequency phasor has a phase shift of minus j. So this minus j means it's rotated by or phase angle of this phasor at t equals to 0 is minus 90 of this positive frequency phasor, and the negative frequency phasor has a phase shift of j, and that is 90 degrees. So if we combine these two together, we have a real signal of sine omega t. Now if we are combining the frequency components of sine omega t multiplied by j, the phasors are rotated by 90 degrees, and then we add the phasors of the cosine omega t, we have a complex signal. So a complex signal has a single-sided spectrum, okay, and the real signals always have the double-sided spectrum. They have the positive frequencies as well as the negative frequencies. So whenever we are talking about the frequency domain, we are actually drawing the components of a real signal in terms of phasors, that this cosine wave can be represented by two phasors rotating in counter rotating direction. This thing is rotating in anti-clockwise direction, this thing is rotating in the clockwise direction. So these are complex signals, and we have seen that using complex signals as our voltage or current sources, our analysis of the AC circuits become quite easier. But behind the scenes, whatever we are doing in the positive frequency, the mirror image is happening in the negative frequency. So I'm going to explain that in a moment. So here if we are representing, this you are going to do this thing in your some other course, such as this is actually a Fourier transform or Fourier series expansion. Fourier was some scientist who gave us a theory that any real signal is actually composed of many phasors in different quantities. So these phasors, if they are positive frequency phasor, they are actually rotating, because we know that the unit of the frequency is cycles per second. So this phasor is rotating at some cycles per second. This thing is rotating a lot quicker. As we go along, like higher and higher cycles per second, the phasors are rotating in faster and faster speeds. And if we combine these phasors together along with the negative frequencies, which are not represented here, but since the signal is real, so if we combine the positive frequencies as well as the negative frequencies together, we have a real signal. So this is, let's take a look at this figure, that this is a real signal. It is composed of these positive frequency phasors rotating in the anti-clockwise direction but at higher speed as we go down the frequency axis, and these are the negative frequency phasors rotating in clockwise direction, going in higher and higher speeds as we move along the frequency axis. So if we add all these phasors together, there's their j parts actually cancel out, and we have the real signal. So but and another thing is that usually, I mean, this figure is known as, or this figure is known as the spectrum, and spectrum represents the constituent components of the real signals in terms of phasors here. So usually the phasors have two things, their magnitude as well as their phase angle at t equals to 0. So what we are going to do is, since it's actually difficult to draw a three-dimensional figure, what we do is that we make two figures. We call something known as a magnitude spectrum, in which we only make the magnitudes of phasors, and then we draw another figure which we call phase spectrum, in which we draw the phase angles of the individual frequency phasors. So usually a spectrum is represented in two figures, because I mean, this drawing a 3D figure with different phase angles is actually quite difficult. Therefore we draw the phase and magnitude spectrum separately. Okay, the last thing is that these phasors, I mean this phasor and this phasor over here, I mean they are not, I mean they have the constant magnitude here, and I mean they have we call these phasors as undamped phasors. And they are not, I mean they are changing in their angles or their positions, but we have what we usually use is the angle at t equals to 0. Obviously they are rotating and they are constantly changing their angles later on, but we are using at their angles at t equals to 0, and we know that they are rotating at certain speed. But the point is that they have the constant radius, so they are not exponentially decreasing or increasing. But these undamped phasors are part of a bigger picture which we call an S-plane. An S-plane is known as the complex frequency. S is the complex frequency, and it has two parts. That's why we have a sigma and we have an omega, and since omega is drawn at 90 degrees here, we just represent it with j omega, and this thing is at minus j omega. So what we were talking about was a I mean j omega means, I mean omega is positive, so this line represents the positive frequency, and minus j omega represents the negative frequency, and this sigma actually represents the exponential variation. So let's take a look quickly here, that whatever we are drawing here, let's say we are drawing at origin equals to 0, at sigma is 0 and omega is 0, so we have no frequency, that means 0 frequency, and we have a DC signal represented at the origin of the S-plane. And if we go along in this direction, the positive j omega direction, but we are on the j omega axis, that means we have a positive frequency phasor, and it's an undamped phasor. I mean the amplitude or the magnitude of, or the radius of this phasor remains constant. If we further move along this y-axis, we have a constant magnitude phasor but rotating at a faster speed. Now if we move along the negative j omega axis, that means we have a negative frequency phasor. It's rotating in the clockwise direction. If we move further along, that means we have a negative frequency phasor, but it's rotating at a much faster speed. Now what if we have a sigma equals to not equals to 0, some positive value? We have an exponentially increasing function, at a much faster rate. And if sigma is negative, we have an exponentially decreasing function, and we have an exponentially decreasing function at a much faster decaying rate. Now if we combine these sigma and j omega variations together, we have an exponentially varying sinusoidal function or sinusoidal phasor, such as, let's say if the sigma is positive and the j omega is positive, we have a positive frequency phasor, but it is increasing in amplitude as time goes on. And here it's same thing is happening. Sigma is positive but a higher rate. This phasor is increasing in amplitude but at a much higher rate. And let's say at this point we have a positive frequency phasor, and it's rotating at omega radians per second in anti-clockwise direction. It's increasing in amplitude at the same time as time goes on. And we have a exponentially decaying positive frequency phasors, and in this thing an exponentially decaying or decreasing negative frequency phasors, and here we have exponentially increasing but negative frequency phasors. They are rotating in the clockwise direction because omega is negative here. So coming back to, I mean this is an exponentially decaying phasor and it's an exponentially decaying phasor, but both of these, this is a positive frequency phasor and this is a negative frequency phasor. So coming to what is actually going on, let's take a look at a simple sinusoidal function, but it has an exponential variation to it. So if we draw an envelope or an outline, so this decaying is controlled by e to the power sigma. and if it's negative, so it's a decaying sinusoidal function. So if I put sigma equals to 0 and omega equals to 0, so we have sigma equals to 0 and omega equals to 0, so we have Vm cos theta. Just it's a constant number, so we have a DC DC source where sigma and omega are 0, so we have no change in the signal, and it's some kind of a constant number. So if we put sigma equals to not 0 but j equals to 0, we have an exponential function, and exponential function is, we know that it increases, or you can just plot it using simple calculator. Now if we have, it doesn't have any sinusoidal variation. If we have a sinusoidal signal, that means that sigma equals to 0 but omega is not equals to 0, we have non-zero, it's a simple sinusoidal signal, so it can be represented as a positive frequency plus some negative frequency, rotating in anti-clockwise direction, rotating in clockwise direction. Now if we just do some simple algebra, so we have, this thing this thing is can be represented by the, this is actually a, this half Em, this is a constant number angle theta and e to the power j omega t. So what are we doing in this phasor analysis we have done so far is that we only consider the positive frequency and we assume that the signal is complex. Behind the scene, what we do in positive frequency, a mirror analysis happens in the negative frequency, because this is a mathematical concept for a mathematical completeness. So whatever we do in positive frequency, a mirror image happens in the negative frequency, and in the end we combine these things together to get up a real solution which is in the form of the sinusoidal forcing function. The sinusoidal forcing function forces the response to be a reflection of itself. So if we have this kind of a forcing function, the unknown voltages and currents in any inductor, resistor, capacitor would have the same form as here. They might have different amplitudes and might have different angles, but the form of the solution reflects the forcing function form. So here this thing, we can represent half Vm e to the power j theta is k1, and this k2 is this thing, and k1 or k2 are conjugates of each other. Similarly, if we draw s equals to j omega, then s2 equals to minus j omega, and s1 and s2 are the conjugates of each other. And lastly, if we have a exponentially damped sinusoidal case, that means sigma is not equal to 0 and omega is not equal to 0. So we can represent this this signal as the summation of two positive and negative frequency phasors along with the exponential variation. So we can represent this, this is the phasor half Vm e to the power j theta, that is we represent as some magnitude angle theta, and this is e to the power st. So this is a positive frequency phasor with the exponential variation which we saw here, a positive frequency phasor with exponential variation. It might be positive, it might be negative. Usually they are negative for stable systems. And coming back to here, this is the negative frequency phasor, and here S1 and S2 are conjugates of each other. So that means coming back to here, we have a negative frequency phasors, which is essentially a mirror image of this thing. So whatever analysis we do in the positive j omega axis or in the second quadrant, this same analysis happens in this quadrant as well. So we only consider this thing, but it is understood that whenever we are talking real signals are composed of positive as well as negative frequency. And keep in mind that negative frequencies is just a mathematical concept for mathematical completeness. So whatever we do, if we, going back to here, that whenever we are talking of real signals, it is understood that negative frequencies are already present in this wave. We do not draw them, but there's understood that the mirror image of all this positive frequency phasors, they are available in the negative frequency axis as well. Now coming back to this thing, we just define complex frequency is small s equals to sigma plus j omega. Do not confuse it with complex power, because that is represented by capital S. And this complex frequency, why we represent this sigma plus j omega with frequency, because frequency is concerned with change, and only thing which controls the change of this signal is sigma and omega. You increase the value of omega or increase the value of sigma, obviously the signal would be changing at a much quicker pace. And if you decrease the values of these two or make them 0 or minus, you change the rate of you change the pace of change of this signal. So we associate with this thing, with the frequency, and the sigma is drawn on the x-axis, and omega is drawn on the y-axis over here. This here. Okay, omega is drawn on the y-axis and sigma is drawn on the x-axis in the complex frequency plane. Coming to the last thing is that if we have resistors in frequency domain, Vs equals to Ris, It is transformed to I of S, and this is exactly the same thing if S equals to j omega. So far the analysis we did was, we only considered the j omega, we did not consider the sigma. So if you replace S equals to j omega, so we are doing analysis in the undamped j omega axis. So we have the same thing as V of j omega divided by I of j omega is resistance, and if we are talking about inductors, then V upon I is the inductance, is the impedance of the inductor SL. If we replace S equals to j omega, that means we are talking undamped phasors, with no exponential variation. So Z of j omega becomes j omega L ohms. And lastly, if we are talking about capacitors in the S domain, so if we take the derivative, so we have the impedance of the capacitor is 1 over SC, and if we replace S equals to j omega, we have 1 over j omega C. And in both of these cases, we were assuming the zero initial energy stored in the inductor as well as zero initial energy stored in the capacitor. Lastly, usually we call this j omega axis as the Fourier axis, just Fourier. That's the name of the person who gave us the Fourier transform and the Fourier series. So we usually, whenever we are talking Fourier analysis, we are actually representing signals in terms of their undamped phasor constituents. So undamped phase, this is actually the plus j omega axis on the S plane, and here that would be this is the y-axis actually on the S plane, and this is the negative y-axis on the S plane. So we usually represent, whenever we are talking Fourier series or Fourier transform, we are actually representing a signal as a summation of many undamped phasors. So if we know the behind the story why we do this phasor analysis is that if we know what would happen if we apply a single frequency to a AC circuit, and we know the response. So what if we apply this kind of a complicated looking signal to the AC circuit? Obviously it's not a sinusoidal signal, it's not a DC signal, it looks kind of a rectangular wave, but it's not exactly a rectangular wave. So if we apply, it has a DC component as well. So if we apply this signal to the circuit, what would be the result? So we know the principle of superposition, that if we know the response of a single phasor, and let's say this signal is composed of a DC phasor, it's not rotating, this it has frequency of 0, this phasor, and this phasor. Let's say it has 3 positive frequency phasors, 3 negative frequency phasors, and a DC phasor. So we already know the DC analysis, we already know what would happen if we apply a single frequency to the circuit, we can know what would happen if we apply only this frequency to the circuit, and we can figure out what would be happening to the circuit if we apply this single frequency. So if we have multiple inputs going there, negative frequency is just assumed to be there. Whatever we do here, the mirror image happens here. So if you're talking, if we know the individual response of each of these phasors, we can add them together, obviously in time domain, not in frequency domain, because they are rotating at different frequencies. So if we add them together in time domain, we can figure out the response of the circuit if we apply this signal. Okay, so we cannot use the normal analysis. How can we figure out that what would happen to the circuit if we apply this, because we do not have even the equation of this circuit, or sorry, this signal. So what can we do is we can resolve this signal into different phasors of different frequencies. These are undamped phasors. So if we apply one of the phasor at a time and figure out the response of the circuit, then we can, using the principle of superposition, we can just add the individual responses of each of these phasors in time domain to figure out the time domain response of the circuit, or time domain response, or any unknown or voltage or current of the circuit if we apply this signal. So that is what Fourier says, that if you have a complicated looking signal, you can represent that as a summation of many undamped phasors. Laplace transform, Laplace is actually Fourier is actually a subset of Laplace. Laplace says that a signal can be represented as a summation of many exponentially varying phasors. Fourier says a signal can be represented as a summation of many undamped phasors. So Fourier works on the j omega axis and Laplace works on the whole S plane.